Alright, I want to talk to you about relating z-scores and area under a standard normal curve. Before we do that, let's start to understand a normal distribution. Okay, um, if we gather enough data, it is likely we will encounter a standard normal distribution. Okay, so what that means is if you gather enough data and make a bar graph, you might see something that looks like this, or make a histogram. Maybe something like that. You can see that most of the data accumulates around the middle, around the mean, and tapers off as you get out here to the edges, right? The number of data values out here should be much less than the number of data values around the average. This forms what we call a standard normal curve, and it looks something like this if we make it smooth and symmetrical. Okay, so this is our standard normal curve. Now, what properties does this curve have? Well, first of all, the area under the curve equals 100% total. Okay, so the all the data is converted to a percentage, and it all fits under this curve. Alright, so we'll kind of see that in practice. The other thing is the mean is in the middle. So if we look at this, our mean data value is right here, exactly in the middle, meaning that 50% of the data is above and 50% of the data is below. Okay? So that means the area, this area that I'm highlighting in yellow, this area is 50%. And the area below the mean is also 50%. Okay? Now, when we think about the horizontal axis, there are data values. The mean is an actual data value. But on a normal curve, we often talk about the data values converted to z-scores. So the mean has a z-score of 0. Remember what z-score is. Let me remind you. Z-score is the number of standard deviations from the mean. So the mean is 0 standard deviations from itself, so we have a z-score of 0. Now if you move to the right, you get other z-scores, like right here you have a z-score of 1. That data value would be 1 standard deviation above the mean. A z-score of 2 and a z-score of 3. You can see by the time you get to a z-score of 3, you have very little of the population that lives that far out from the mean. Now when you move to the left, you get negative z-scores. So 1 standard deviation below the mean corresponds to z equaling -1. Then you've got, of course, -2. Then you've got, of course, -3. Now there are other z-scores here as well. For example, you could say maybe approximately right there you have a z-score of -1.3, let's say. So this is just to give you an idea of a scale, but you have all z-scores on this horizontal axis, and each of those relates to a data value. Okay? Now what I want to do is show you how to use a z-score / area chart, and I've got one made here in Microsoft Excel. Let me see if I can make this fit on the screen a little better. Okay, very good. This chart I made in Excel relates z-scores to areas. So for example, if I look at a z-score of 0.62, that relates to an area of 0.232. That's 23.2%. Let me show you what that means on the curve. So I'll go back to my notes. In the notes, we saw that from the chart, z equals 0.62 corresponded to an area of 0.232. What that tells us in this curve, this normal curve, is that, sorry, that's not great, but you get the idea. We have, of course, the z-score of 0, which is the mean, right in the middle. A z-score of 0.62 is to the right. It's a positive z-score. So z equals 0.62 is right here. So what is this? What is this area, right? So if we were to draw a vertical line from this z-score, this area, this 0.232, is the area between the given z-score, 0.62, and the mean. Okay, so this chart gives us areas between the given z-score, in this case 0.62, and the mean, z equals 0. Okay, sorry, I forgot to mention the word area. So to interpret that, what it means is you have 23.2% of your data is between the mean and 0.62 standard deviations above the mean. Let me type that. So 23.2% of the data values are between the mean and 0.62 standard deviations above the mean. Okay? So that's what this means. That's what the chart tells us. Always measure to the mean. That's what people forget. Always measure area to the mean. Okay? Now it's also true because of the symmetry of this curve. If you go back to the z-score chart, you'll see there are no negative z-scores on this chart. If I scroll, no negative z-scores, okay? That's because this chart is symmetrical. It's also true if I look at negative 0.62, which is exactly the opposite side over here, that this area is also 23.2%. Okay? So what we could say then, another observation we could make is, due to symmetry, we can also say that double that percentage, 46.2% of the data values are within, so that means above and below, or above or below, 46.2% of the data values are within 0.62 standard deviations from the mean. Okay? So things like that are important. We could also say something like if this area here is 23.2% and from the mean all the way to the right is 50%, then the area in this green region here would be 50% minus 23.2%, which is 26.8%, I believe. So now, if we were to describe that in words, we could say 26.8% of the population, or of the data values, of the data values, let me shrink this so you might be able to see the picture too, are above, or let's say it this way, more than 0.62 standard deviations above the mean. So we can get so much information from this chart, but the area that the chart gives us, is the area from the data value back to the mean only. But you can see, because this chart is symmetrical and because half of the chart is 50%, you can get a lot more information than just the area that's given. Okay, so that is how to interpret this z-score area chart for normal distribution.